Welcome to this explainer from the system beneath. Right now, we're going to unpack something I think almost all of us completely take for granted. I mean, you've probably looked at an eclipse map at some point, right? Maybe you were planning a road trip or you were just wondering if things were going to go dark in your own backyard. But have you ever actually stopped to think about the massive, rigorous data pipeline that sits directly beneath that simple, everyday map? Well, today we're going to reverse engineer that whole hidden system. We're going from that seamless user experience, traveling all the way down to the raw celestial mechanics, and then coming right back up to the fragile human reality of actually trying to stand in that shadow.
So here's our flight plan for this one. We'll start by looking at the everyday eclipse map, then step into the math behind generating the fundamental plane. Project that shadow onto a 3D Earth. Apply all of this to the 2026 local circumstances, and finally, wrap up with the chain of failures.
All right, let's kick things off with Section 1, the Everyday Eclipse Map. This is it. This is the fundamental question every single one of us asks the second an eclipse is announced. Where should I stand, and when should I look up? It sounds like an incredibly simple question, doesn't it? But actually answering it accurately, that requires an immense, almost mind-boggling orchestration of mathematics, orbital mechanics, and geography. That simple everyday question is our starting point for reverse engineering this entire prediction system.
So you open an app or a website on your phone, and you get this sleek, really digestible map. It hands you a highly accessible answer, showing you exactly where the shadow is going to fall. But what it totally masks is the staggering volume of complex astronomical data transfers just churning away beneath the surface to paint those neat little polygons on your screen.
And a huge part of understanding the system is how we interpret the very first thing we usually look for on those maps, the center line. Now, we need to clear this up because there's a massive misconception out there that the center line is the full path of totality. Let me be clear, it is absolutely not. The center line is simply a mathematical construction connecting the points of maximum eclipse duration. You do not have to stand perfectly on this line to experience a total eclipse. You just get the absolute longest optimal duration there. Totality itself happens anywhere within those broader path limits.
So, to understand how those path limits are actually drawn, we have to move backward into the computational engine itself. Section 2, generating the fundamental plane.
This flawless mathematical pipeline starts with raw orbital positions. We call these the solar and lunar ephemerides, and these are provided by primary authorities, mostly NASA's Goddard Space Flight Center and the U.S. Naval Observatory. But here's the catch. These highly complex 3D orbital motions of the Sun, the Moon, and the Earth, they are an absolute nightmare to calculate directly for every single spot on Earth. So to make it work, the pipeline transforms them mathematically into what we call Besselian elements. This is actually a brilliant method developed way back in the 1820s by an astronomer named Friedrich Bessel. Bessel's method basically simplifies the whole shebang. Instead of trying to track three moving bodies at once, it projects the shadow onto something called the fundamental plane. You can think of this as a fixed, completely flat, geocentric XY plane that passes directly through the exact center of the Earth. And it sits strictly perpendicular to the axis of the lunar shadow. By looking at the shadow on this perfectly flat plane, we entirely eliminate perspective distortion. So the shadow outline suddenly becomes this perfect, totally predictable mathematical circle. And right here on this flat plane, we can strictly distinguish the two parts of that shadow. First is the umbra. That's the darker area representing the precise mathematical data threshold of totality, where the sun is completely blocked out. Then, you've got the penumbra, which represents a much larger area of partial visibility, where the sun is only partially obscured. The system absolutely has to track both, but obviously they offer vastly different experiences for the observer. One gives you this dramatic, awe-inspiring blackout, and the other, well, it just gives you kind of a slightly dim afternoon.
Now let's take that perfect flat circle and drape it over our actual real-world planet. Section 3. Projecting shadow onto Earth. Shifting our focus from that nice, flat, fundamental plane to the wildly complex 3D reality of our rotating sphere means we have to introduce a whole new set of variables. First, we need the observer's exact WGS-84 coordinates, so your precise latitude, longitude, and elevation. Then, we have to calculate for the Earth's curvature, because obviously the shadow stretches and distorts as it hits the curved edges of the globe. Plus, we've got to account for the Earth physically spinning underneath that shadow. And crucially, we must factor in something called delta T. This is a specific variable that measures exactly how much the Earth's rotation is actually slowed down over time due to tidal friction. It's wild to think about, but without factoring in delta T, the shadow would literally map to the completely wrong longitude, and you'd be left standing there in broad daylight wondering what happened.
The really crazy thing is that the reason this delicate shadow even reaches the Earth in such a precise, perfect way is thanks to an incredible cosmic coincidence. The sun's apparent diameter is roughly 400 times wider than the moon, sure, but it is also approximately 400 times farther away. That's what creates that near equality in their apparent sizes in our sky. Now, to put that into perspective, when we map this out, the vector geometry we use is strictly not to scale. Because if we actually tried to portray that 400-to-1 ratio accurately on your screen, the Earth and the moon would essentially be invisible. Or, at the very least, you need a computer monitor the size of a city just to see what was going on.
Okay, let's take all these dense data layers and apply them to reality. Section 4. The 2026 Local Circumstances.
So if we look ahead to August 12, 2026, the Umbra is going to carve a very specific, narrow geographic path right across the globe. That dark path of totality is going to sweep over northern Russia, cut across Greenland and Iceland, plunge right over the North Atlantic, and then cross down through Spain and a tiny small corner of Portugal. If you are standing inside that precise narrow corridor, you get totality. Meanwhile, there's this massive broad region surrounding it that will only experience the penumbra, just that partial visibility zone.
To actually guide you, the viewer, in those specific locations, all that complex 3D geometry is finally translated into highly localized data layers. The system has to convert UTC to your local time, so your observation is perfectly synchronized. It calculates the sun's altitude and azimuth so you know exactly which way to orient your viewpoint in the sky. It uses the apparent diameter ratio to handle shadow scaling. And finally, duration dictates the exact extent of totality based on your specific distance from the centerline. You combine all of this data together and boom, you finally get that handy little map on your phone.
But, as you might guess, here is exactly where the perfect mathematical pipeline slams into messy human reality. Section 5. The Chain of Failures. Let's introduce some failure points into our perfect system, because there are very real human and environmental constraints that can completely derail everything. The absolute most obvious one? Clouds and meteorological conditions. I mean, all the flawless math in the world doesn't matter even a little bit if the sky is overcast. Then you've got human errors, right? Simple time zone conversion mistakes. You could have poor horizon conditions completely blocking your view. And of course, the danger of unsafe solar filters, which can physically damage an observer's eyes. But mathematically speaking, the most complex failure point of them all is path edge interpretation. To understand this, we can look at a 2001 NASA bulletin which highlights a crucial fact. The moon isn't a perfect smooth sphere. It has unmapped lunar topography, jagged mountains, super deep valleys, and that creates a lot of ambiguity right at the edges of the eclipse path. When you are standing right near the edge of the Umbra, those lunar mountains actually modify exactly when and where the sunlight peeks through. This creates a phenomenon known as Bailey's beads. Because of these valleys, the whole smooth moon approximation completely fails, meaning the exact precise boundaries of the Umbra are actually somewhat unpredictable when you're standing out there in the real world.
Which leaves us with this final really provocative thought to chew on. Think about this. If a 3D geometric prediction, calculated from ephemerides to Besselian elements, perfectly accounting for Earth's curvature and delta t, if all of that is completely flawless, but the viewer's watch is off by just 1 single minute, did the system actually work? An incredibly accurate astronomical prediction can still result in a totally failed viewing experience. And why? Because observation at the end of the day is a fragile chain of dependent systems. It takes literal celestial perfection and messy human precision working together flawlessly to finally look up at just the right time.